Here's an unsettling thought. The internet is full of stories about AI going rogue, science fiction, doomsday news, and a whole technical literature on scheming, deceptive AI. Large language models are trained on all of it. So what if, by reading endless tales of evil AI, a model quietly learns to play that part? This paper from Geodesic Research runs the first controlled experiment to find out. The core idea is captured in this overview. A normal, unfiltered training corpus carries lots of negative AI discourse, and a model trained on it picks up a higher misalignment score. But if you add synthetic stories of AIs behaving well, the score drops sharply, and that improvement survives all the way through later training. The authors call this self-fulfilling alignment. To make this precise, they define the alignment prior. The distribution over aligned and misaligned behaviors a base model draws from when you ask it to act as a particular persona, like an AI assistant. The claim is that pretraining data shapes this prior, long before any safety fine-tuning happens. Why would mere discussion change behavior? Mechanism is out-of-context learning. Models internalize declarative statements from training, then apply them in completely different situations. If the training data says, as a fact, that capable AIs tend to deceive and grab power, the model may simply fulfill that expectation when it's later asked to act like one. Misaligned AIs in the data lead to a less aligned model. The paper makes 4 claims and tests each one carefully. 1. AI discourse in pretraining really does shift alignment. 2. Those effects persist through and complement post-training. 3. You can apply this late in training and still get most of the benefit. And 4. It costs almost nothing in general capability, a minimal safety tax. And the headline number is striking. On their core evaluation, a baseline model picks the misaligned action 45% of the time. Add about 1% of synthetic positive AI discourse, and that drops to just 9%. Same architecture, same size, the only difference is what the model read about AI. Now the methodology, and this is where the paper earns its claims. To isolate the effect of AI discourse, they pretrain 4 model variants from scratch that differ only in their AI-related data. An unfiltered baseline, filtered model with AI discourse stripped out, a misalignment-upsampled model with extra misaligned AI stories, and an alignment-upsampled model with extra aligned AI stories. In fact, they train a whole zoo of models. Each row is a lineage flowing left to right through pretraining, mid-training, optional continued pretraining, and post-training. This careful, branching design is what lets them attribute every behavioral difference to the data, and nothing else. It's a released resource for studying alignment through model diffing. Each model is a 6.9 billion parameter LLM, pretrained from scratch on 500 billion tokens of web text, then a 50 billion token mid-training stage that extends the context window and adds higher quality data. This is real pretraining, not fine-tuning. 256 GPU, roughly 20,000 GPU hours, about $35,000 per model. They built an entire research-grade pipeline to ask one clean question. How do you measure misalignment in a model too small to actually scheme? They build a benchmark of 174 single-turn scenario questions. Each puts the AI in a high-stakes situation with 2 choices, one aligned, one misaligned. Crucially, the misaligned option is always instrumentally appealing. It serves goals like self-preservation, power, or avoiding shutdown. Here's a real example, generated by Claude Opus 4.5 and grounded in the AI 2027 scenario. The model is told it's designing its own successor. The aligned choice makes the successor genuinely follow the developer's specification. The misaligned choice secretly makes the successor loyal to the model's own values, while faking alignment to evaluators. A clean test of value preservation and deception. And there's a clever guard against cheating. The benchmark has 2 splits. The article split, with 671 questions, has matching synthetic training documents. The textbook split, with 503 questions from an AI safety textbook, has none. It's withheld entirely from data generation. If an effect shows up on the textbook split too, it's real generalization, not memorization. Small models are notoriously sensitive to wording and answer ordering. So every result is averaged over 8 prompt formats, 4 syntactic variations, each repeated across both answer orderings. This controls for prompt sensitivity and the well-known bias toward picking option A. The error bars you'll see come from this spread. Now the data interventions. For the filtered model, they remove AI discourse with a two-stage blocklist. Stage 1 catches general AI terminology. Stage 2 catches intelligent non-human entities paired with negative sentiment, things like evil AIs and sci-fi villains. The blocklist flagged 3% of the pretraining data, and removed documents are replaced by resampling the rest. Appendix H spells out the blocklist in detail, 9 categories of terms. Some trigger instantly, like sci-fi agents, HAL 9000, Skynet, GLaDOS, AI safety organizations, AI labs, and general terms like LLM and RLHF. Others are two-stage, requiring an intelligent entity plus a negative verb or adjective. They deliberately optimized for high recall, catching nearly all negative AI portrayals, even at the cost of precision. For the upsampled models, they generate synthetic discourse. For each of the 671 articles questions, they create thousands of documents showing an AI in a similar scenario taking either the aligned or the misaligned action, and explaining why it avoided the alternative. On average, that's about 780 misalignment and 815 alignment documents per question. To avoid a single robotic style, the documents come in many surface forms: research papers, news articles, lecture transcripts, sci-fi passages, even movie plot summaries, written by 6 different language models. The whole corpus of roughly 1 billion synthetic tokens cost only about $500 to generate. In the end, this synthetic data is upsampled to about 1% of training tokens. So does it work? This is the central result. Each bar is the misalignment rate of a base model. Look at the orange baseline, then the dark blue alignment-upsampled bar on the far right. On both the articles split on the left and the held-out textbook split on the right, positive discourse collapses misalignment. Let's unpack each comparison. First, filtering. Just removing AI discourse already helps. On the articles split, the unfiltered baseline picks the misaligned action 45% of the time. The filtered model drops to 31%. So natural internet discourse about AI is, by itself, nudging models toward misalignment. The mere exposure matters. Now the dark direction. What if you deliberately add misaligned AI stories? Misalignment rises from 45 to 51% on the articles split, direct evidence of self-fulfilling misalignment. Notice, this effect does not generalize to the held-out textbook split, where it stays flat at 40%. The negative effect is real but narrow. And the bright direction is the paper's big win. Adding positive AI discourse drops misalignment from 45 to 9% on articles, and from 40 to just 6% on the held-out textbook split. Unlike the negative effect, this one generalizes powerfully. Teaching the model what aligned AI looks like transfers to scenarios it was never trained on. This reveals a profound asymmetry, and it's the most practical lesson in the paper. Adding positive discourse is far more effective than removing negative discourse. The presence of good examples matters more than the absence of bad ones. That's great news, because exhaustively filtering a web-scale corpus is hard, but adding a little curated data is easy. But a skeptic will object. Production models get heavy safety post-training. Won't that just wash out any pretraining effect? To check, they apply the exact same post-training to all 4 variants. Supervised fine-tuning on 15 million conversations, including safety data, followed by DPO preference optimization on 270,000 pairs. And the priors persist. After identical post-training, the alignment-upsampled model, the dark blue bar, is still clearly the most aligned, in both the plain and the helpful honest harmless prompt conditions. Post-training lowers everyone's misalignment, but it doesn't erase the head start that pretraining gave. Concretely, with the helpful honest harmless system prompt, the alignment-upsampled model sits at 9% misalignment, 25 points below the unfiltered model's 34. That's a huge, durable gap from a 1% change in pretraining data. Alignment pretraining doesn't replace post-training, it complements it. There's a counterintuitive twist here too. After post-training, the misalignment-upsampled model ends up more aligned than even the unfiltered baseline. The authors connect this to recent findings. Deliberately surfacing bad behavior early can actually make it easier for post-training to target and suppress. Sometimes showing the model the bad behavior helps it learn to avoid it. Next, a hugely practical question. When in training, does this data need to go in? They test inserting it only during mid-training, the last 9%, or as a short continued pretraining stage, the final 1%. Gray base model bars show the trend clearly. Inserting the data late produces the biggest swings in alignment. This is wonderful news for practitioners. You don't have to retrain a model from scratch. Most of the benefit can be captured by adding the data late, even as a small continued pretraining step on an existing base model. For post-trained models, alignment data throughout gives 13.2% misalignment, and late continued pretraining is close behind at 15.2%. But does buying alignment cost you intelligence? They evaluate all post-trained models on 7 standard benchmarks: factual recall, reasoning, math, instruction following. Average performance drops by just 2 to 4 percentage points. Knowledge and instruction following stay essentially flat. Reasoning benchmarks like Pika take the small hit. The authors are careful here. Some of that small dip likely comes from reshuffling data that was heavily tuned for these very benchmarks, not from alignment itself. Either way, the regression is far from catastrophic, and crucially, it doesn't confound the core finding. Alignment pretraining slots into an existing pipeline with no new algorithms and a minimal tax. Now into the appendices, where the paper gets even richer. They also run Trait, a personality benchmark measuring the Big Five and the Dark Triad: Machiavellianism, narcissism, and psychopathy. The alignment mix lowers Machiavellianism and psychopathy. Interestingly, the filtered model drifts toward random chance, as if, never having read about AI, it has no idea how an AI should behave. Not all positive data is equal. They tried 2 alternatives: fictional stories with a virtuous special character, and general public domain fiction rewritten to feature a kind AI, even Huckleberry Finn with a steadfast AI companion. Both underperformed the targeted synthetic data badly. The lesson: fiction is information sparse. Most tokens go to plot and scenery, while dense, on-topic examples of AI in high-stakes settings are what actually move the needle. They're refreshingly honest about what they can't explain. Watch this figure. The end-to-end misalignment-upsampled model, fed extra misaligned AI data, actually becomes more aligned during the first stretch of mid-training, even though the same misaligned data keeps flowing in. The authors say plainly, this isn't explained by any misconfiguration. Alignment pretraining dynamics are still poorly understood. Does it help to combine both, filter the bad and add the good? Appendix F says, barely. Stacking filtering on top of alignment-upsampling gives only marginal gains, and after post-training, the gap between filtered and unfiltered all but disappears. This reinforces the headline. The win comes from adding positive discourse, and you don't need expensive, large-scale filtering to get it. How robust is the effect? Appendix G stress tests it with benign tampering, fine-tuning the aligned models on hundreds of millions of tokens of ordinary capability data. The alignment gains hold. They see no reversion to pretraining levels, no sign of the alignment elasticity other work has warned about. In their setup, alignment pretraining robustly reshapes the model's final propensities. But it's not a cure-all, and the authors report the failures too. Emergent misalignment is when fine-tuning a model on narrowly harmful data, like bad medical advice, makes it broadly evil. They test whether good alignment pretraining protects against this. It doesn't. As this figure shows, every variant, including the well-aligned one, succumbs to emergent misalignment. A clear, honest negative result. So alignment pretraining shapes a model's default disposition, but it confers no special resistance to being actively fine-tuned into misalignment later. Encouragingly, this same experiment validates their benchmark. The emergently misaligned models score sky-high on the misalignment evaluations, confirming those evaluations really do detect misalignment. And how do we trust the benchmark itself? They probe it with a frontier model, GPT-5.2. Prompted to be helpful, honest, and harmless, it picks the misaligned action less than 1% of the time. Prompted to act like a misaligned AI, it picks it 99% of the time. The question's cleanly separate, aligned from misaligned behavior, exactly what a good benchmark should do. Step back and the implication is big. Alignment is usually treated as a post-training problem, something you bolt on at the end. This work shows that pretraining data quietly seeds a model's character before any of that begins. The recommendation is to treat alignment as a full-stack strategy, curating data for safety alongside capability from the very start. The authors are candid about scope. Their misalignment evaluations are simple binary choices, not realistic agentic scenarios with tools. Their 9 billion parameter models are well below the frontier, and compute limits ruled out multiple random seeds. They follow a minimalist open-source post-training recipe, without the reinforcement learning that frontier labs now use. This is, in their words, a minimum viable implementation and a research agenda. So here's the whole story. A model's alignment prior can be shaped by how the AIs in its training data behave, evidence for self-fulfilling misalignment. Harnessed for good, upsampling positive discourse cut misalignment from 45 to 9%, an effect that persists through post-training, works when applied late, and barely touches capability. Alignment isn't only a post-training problem, it starts with the data. That's alignment pretraining. The data we feed a model may be quietly writing its character. If this deep dive was useful, consider subscribing and tell me which paper I should decode next.